Okay, so last meeting, we have been discussing the basics of evaporation. So we have defined it. We look into the different liquid characteristics. We look into the different phenomena that will be happening inside our evaporator. And we ended with the different evaporators classified according to the manner in which the feed may be introduced into it, or characterized or classified in the manner in which it's being operated. Now, we have two schemes for the way we concentrate the feed for evaporators, and that is it could be single effect or multiple effect. And each of those two schemes, we have several evaporators to use depending on the kind of feed that the evaporator has to handle. So our evaporators have their specific applications, so please remember those applications. Now, this is the part which we ended in the first discussion, and this gives you the performance measures of evaporators. So we have number one is its capacity to evaporate water for the solution or for the feed that is to be concentrated. And second, this is referred to as actually as steam economy, which can also be defined as evaporator economy. So this is the kilograms of water vaporized per kilogram of steam used. In the case of the capacity of the evaporator to evaporate water is measured in terms of mass of water evaporated per unit time. Now, the amount of steam that is consumed by a particular evaporator for a given duty that it performs is actually taken from these two. So if we divide the capacity by the economy, we'll be able to determine the steam consumed by the evaporator, and that is kilogram of steam per unit per hour, or that's mass of steam per unit time. So this is where we ended, and I'd like to go to the intro part of the calculation for evaporators, and that is focusing on the main reason why the evaporator is able to concentrate the solution or the feed, and that is the temperature gradient, which is the driving force. Now, this temperature gradient or driving force is the difference of the temperature of the steam and the temperature of the feed inside the evaporator. In some problems, it is referred to as the vapor space temperature. Now, if it is then the vapor space temperature, we can base this particular temperature on the operating pressure of your evaporator. Meaning, if the problem does not give you the boiling point of the solution, you can still find it if the problem is giving you the operating pressure of the evaporator. Based on that operating pressure of the evaporator, you go to your steam table and find the corresponding saturation temperature at that particular pressure. That is now the vapor space temperature if your evaporator does not have boiling point elevation. Now, I will discuss that later. So this is in the normal sense wherein the feed does not have boiling point elevation. The vapor space temperature is the saturation temperature at the indicated pressure. That is indicated operating pressure of your evaporator. Now, this driving force will lose its essence or will not be capitalized on if the boiling temperature of the feed inside the evaporator is increased. Why is that? We're going to subtract in the first place the boiling point temperature of the solution from the temperature of the steam. So if the one that is being subtracted to the temperature of the steam is increased, then the difference between the two is decreased. So if the difference between the two is decreased, then we're saying that the driving force, the temperature gradient, was also decreased. If it is decreased, then it boils down to Q being decreased as well. And that is the rate of heat transfer being decreased. Now, in your handbook, you have the BPR of commonly vaporized or concentrated aqueous solutions. And it's found in figure 11-124 of your handbook. I'd like to go to that illustration now. That way I can already explain how is it or how you're going to find the BPR or the boiling point of the solution based on that particular um, figure. But the thing is, I can't transfer. Why is it that I can't transfer? Wait, class. Anyway, I'll finish this, then I'll transfer later to that illustration for the BPR of an aqueous solution. Now, if the solution is not aqueous, if it's a solution of inorganic salts, in your handbook, you can also use equation 11, thus 1, 2, 3, in determining the boiling point of such solutions wherein you have the presence of inorganic salts. However, you are to take note of that that particular boiling point is at atmospheric pressure. So meaning at elevated pressures, this equation will not work anymore. It's only good for the condition at atmospheric pressure. Now, for other pressures, since we are only limited to atmospheric condition for both figure 11-124 and equation 11-123 in your handbook, there is a corresponding correction factor for that. That particular correction factor should be made known or should be specified in the problem so that you can apply such correction factor in terms of the correct boiling point of your solution later on. So if the problem does not say that there has to be a correction factor, it's okay. It's okay to assume that your boiling point is based on the atmospheric pressure or your evaporator is operated at atmospheric pressure. Now, in terms of the phenomena of entrainment, which I have mentioned already in the first set of slides, there is this corresponding allowable velocity that if will not totally eliminate the problem of entrainment, but it will not cause it, or it will lessen the problem of entrainment. And this particular equation is by Saunders-Brown. So it gives you the formula here for determining the velocity, allowable velocity that will lessen entrainment or that will not cause it totally. So not only entrainment, splashing and foaming can also be addressed if velocity is contained up to this value. So in this formula, you have the K, a constant that depends on the size distribution of the droplets, and the decontamination factor F, which I will show to you in a little while. So this K has to be determined based on the decontamination factor F. The rho L and the rho V are densities of the liquid and the vapor. So you only need these two because anyhow this one, if given by the problem, will simply be substituted in the formula. If not, you have a separate formula for the K. So that would now give you the velocity that will not cause entrainment or that will lessen or decrease entrainment. How do we determine K? So for most evaporators, the decontamination factor is within the range of 100 to 10,000. So it has to be specified in the problem what is the corresponding decontamination factor. And once it's stated there, you can determine already this K because you need to substitute it in the formula. The K that you're getting here, you substitute on the formula in this slide to get the allowable velocity that will not cause entrainment. Although you can still read suggestion on section 11, that's 112 on your handbook on how to reduce, prevent foaming, product loss, and splashing. And that would be based on your free time already on when you're going to find the time to read such suggestions on the manner of reducing or preventing product loss caused by foaming, splashing, and entrainment. So just visit or get a hold of a copy of your handbook. By the way, the handbook that I'm using in this set of slides then is the 8th edition. I haven't yet changed to the 9th edition here. But in some cases, what you have on the 8th is exactly the same on the 9th edition in terms of the section. So probably it will maybe displaced only in the section number, but it's still the same section. Now, in terms of evaporator arrangement, we know that we can operate it singly or we can operate it in multiple scheme. But there are particular feed, especially the fruit juice that needs to be concentrated for those fruit juices that needs to be in powder form. And in this case, they are really very temperature sensitive, and as such, they need to be concentrated at low temperature. Now, there is this particular heating fluid that is being used for such evaporators, which is the freon or ammonia. It's a secondary fluid, so meaning you're still using steam, but after the evaporator has already reached a certain temperature, then they use freon or ammonia. Now, probably some of you may find this ironic because freon and ammonia are refrigerants. They are used by cooling systems, uh, refrigerator rooms, refrigerators, air cons. But in this case, these particular freons are being used as secondary heating medium. How is that? So ironic, but it can be done. So in this case, the vapor is condensed in an exchanger cooled by boiling freon. The vapor coming from the evaporator that is using this freon as a secondary heating medium is being condensed and cooled down by boiling freon. After that, the freon has been used in condensing the vapor. It is being compressed because of its high vapor density. It is being compressed to serve as the heating medium for that same evaporator. The freon is used, the boiling freon is used to condense the vapor for a particular evaporator. After it condenses the vapor, it is being compressed and again reused in that same unit as the secondary heating medium. That's in the case of using freon and ammonia as a secondary heating medium. For evaporator calculations, refer to the sections in your handbook. And for a particular type of evaporator known as flash evaporators, you have these unique equations, equation 11-124 and 11-125, that will determine the steam economy and the mean effective temperature difference available for heat transfer. Now take note, these equations are only for flash evaporators. The rest of the evaporators are governed by the same set of equations. Now, our evaporator has accessories. The primary accessory is the condenser, the one responsible in converting the vapor into liquid, the vapor coming from the concentrated feed. Now, the condenser used in our evaporator can either be barometric condensers, or the one that referred to as the direct contact condensers, or the surface condensers. In the case of barometric or direct contact condensers, the vapor and the liquid that is to be used as coolant are mixed directly. So there is direct mixing of the vapor and cooling liquid, and as such, the vapor is condensed. In the case of the surface condenser class, the condenser is in the form of a shell and tube heat exchanger. And we're done with this. Now, the vapor that is to be condensed flows outside the tubes, or flows on the annular spaces outside of the tube, and the cooling medium flows inside the tube. Now, this is much more expensive than the other types of evaporator. Now, another accessory that is being used is the vent system. Now, these vent systems are being used when in the process of evaporation, non-condensables are forming. So these non-condensables later on will impede heat transfer. So that is why there's a need for them to be vented out. And the vent system is the one that is responsible for this. For the salt removal system, this is in the case of unavoidable formation of salts or incorporation of salt in your solution to be concentrated inside the unit. So there has to be this particular settling zone for these solids, these salts, to be later on collected and removed from your unit. Now, most of the evaporator problems which determines or asks for the amount of water that is to be supplied by the condenser so that it is able to condense the vapor is this equation. So, and this is used for a barometric condenser. So in here, you are determining water flow ratio with vapor flow ratio based on the enthalpies of the streams that are present in your condenser. So HV is the vapor enthalpy, which you can get from the steam tables. And H1 and H2 is the water enthalpies of your cooling water. So if you get these enthalpies from appropriate table, since most of the time this is just water, so you can get it from the steam table, and you have already predetermined the value of the vapor, the V, through material balance and energy balance, then you can determine the amount of water that your condenser is using so that it will be able to condense the vapor that is fed to it. So water flow for the condenser is solved using this formula. That is for a barometric condenser. Now, I have mentioned already this vent system, so that's for non-condensable. It addresses the issue of the non-condensable because they impede heat transfer, especially if their concentration already increases. In the salt removal, so in the case of evaporators that are also functioning as well as crystallizers, so they are referred to as evaporator crystallizers, there's a need for a salt removal system or a setting space, as I have mentioned already, for these particular salts to be removed later on from your system. Now, uh, in the manner we operate our evaporator, there are two principal elements. Normally, we ask for evaporation rate and we ask for the rate of product removal, or in terms of quality, its concentration. So what is the evaporation rate and the concentration of the product that is withdrawn aside from its quantity, or that's the letter L. So we effect control on the evaporation, or we can control the rate in which water is vaporized through steam flow control. And since steam is the most of the time the heating medium that is used, if we want to properly control the evaporation rate, then we control the steam flow. Now, if you want to effect control on the concentration of the product, that is, if you want to increase or improve the concentration of the thickened liquor in terms of its solid content, then we control the rate of product withdrawal. Meaning, we don't really remove everything all at once. Like the concentrated liquor are all removed, then the next set of fluid that is concentrated and is constantly removed. In some cases, and I have mentioned this in the other types of evaporator that I have discussed in the previous discussion, there is this particular settling zone inside the column, or a zone wherein a portion of the thickened liquor is kept inside in a form of a pool of liquid. It's a pool of liquid inside the evaporator wherein part of the concentrated product is kept. So as a process, since it undergoes subsequent and prolonged evaporation, its concentration is enhanced. So the quality of the final product that is withdrawn is much better or higher in terms of concentration than compared to a particular evaporator wherein the feed only undergoes once through evaporation. Meaning, kaisa lang siya evaporate, then you now get the concentrated product. So in the case of an evaporator which has a pool of concentrated liquor inside, prolonged heating allows us to improve the concentration of the product. So that's how we control the concentration of the final product for the evaporator. So there is this reiteration before I go to the sample problems and computation for evaporator. The capacity is kilogram water evaporated per hour, and the steam consumption is kilogram steam used per hour, which was already discussed in the previous slide. This is capacity divided by economy. And now we go to calculations for single effect evaporation. So if this is your evaporator, there's a very simple illustration of evaporator. You have a rectangle. You have your feed, you have your steam, you have your vapor, you have your liquor, and you have your condensate. Um, The reason why the condensate here is labeled also as S is because the amount of the C, the condensate, is the same as the amount of the S. The only difference is their phase or their form. This one is vapor, this one is liquid. So you have the temperatures of the streams here, you have their mass fractions, and you have their enthalpies. Okay? Now, the enthalpy of the vapor can be of two forms. It could be the simple saturated vapor enthalpy if your solution does not have boiling point elevation. It would be a superheat. We call it a superheat, or it will include the superheat if your solution inside will have already what we call boiling point elevation. So it can have two forms: saturated vapor enthalpy only, or saturated vapor enthalpy plus the, shall we say, the superheat, because you have already boiling point elevation. Now, as for the enthalpy of the feed, it's either taken from an enthalpy concentration diagram, or it can be solved using a standard formula that you have already encountered in thermodynamics, which I will be showing to you in a little while. A simple case of heat capacity multiplied to difference in temperature. Okay, the steam enthalpy is the saturated vapor enthalpy at the indicated temperature or pressure of the steam. Now, this one, since this is condensate, this would be the saturated liquid enthalpy at the indicated temperature or pressure also of the steam. The concentrated liquor enthalpy will be taken from the concentration diagram for the particular, let's say, system that you are concentrating, because we have different concentration diagrams for different systems. Now, XL is still the concentration in terms of mass fraction solids for your thickened liquor. That is same concentration inside. Now, T1, 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 meaning these three have the same temperature. This T1 is based on P1. It is the saturation temperature at the indicated operating pressure of your evaporator. Now, I have mentioned a while ago that the capacity of the evaporator is measured in the amount of water that it vaporizes per unit time. That is if the problem specified that determine the capacity of the evaporator in kilogram per hour, then it's referring to the amount of water that it is able to vaporize per unit time. But if it's talking about capacity in terms of the amount of heat that the steam is supplying to it so that the feed is to be concentrated, then we go back to this very basic fundamental equation for heat transfer, rate of heat transfer. You need to multiply the overall heat capacity, the area, and the delta T to get this rate of heat transfer, or the amount of heat that is transferred. Now, the delta T is the driving force, which I have already discussed at the beginning. So, difference of the temperature of the steam and that of the boiling liquid inside the evaporator. Now, to solve for the Q, this Q here, there's a need for you to do both material and energy balance. Both material and energy balance is needed for the Q to be determined. Unless otherwise that the amount of steam is already known. So if the amount of steam is already known, you only need to get the latent heat of evaporation of your steam. If you multiply it to the amount of steam, that is also the same Q as this one, which I will be showing to you in a little while. Now, most steam tables does not have a column for latent heat of evaporation. They don't have it. So what you do, you get the difference between the saturated vapor enthalpy and the saturated liquid enthalpy. That will give you the latent heat of evaporation of your steam, or of your any fluid for that matter. Now, at equilibrium and steady state, we are only using two material balance equation in evaporation. And that is the feed should be equal to the thickened liquor plus the amount of water vaporized. When we do solute balance or solid balance, then the V is taken out of the picture. If the problem does not mention any entrainment, there isn't any value for the YV because YV will only have a value when there is entrainment, and that is if some solids are carried over by the vapor as it goes up your evaporator. If there's none, and most of the time, 98-99%, most of the time there's no entrainment, then when you balance the solids, then it will only have two terms on the left side and the right side of the equation. Now, you may be saying it's impossible that there won't be any some sort of entrainment. If there is, then the amount entrained, the solids entrained, is negligible, and as such, it's okay to really take out V from the picture when we do solute or solid balance. That is in the case of material balance. When we do energy balance, we get the sum of all energies entering your evaporator and the sum of all energies leaving your evaporator. So then that would mean that you need to add the energy of the feed to the energy of the steam. You equate the sum to the energy of the concentrated liquid, the energy that your vapor has, and the energy of the condensed steam that was already spent out. I mean, its energy was already used up in heating your feed to be concentrated. Now, your main equation would be 3, 4. In terms of the equations that you need to take note of, this number 1, because this one you know already from thermodynamics. So you have 1, 3, and 4. In terms of this last worded equation, the energy balance, this would be it. So energy of the feed, energy of the steam, energy of the liquor, energy of the vapor, energy of the condensate. If we would transfer this SHS on the other side, the S can be factored out and you will have the difference of the capital HS and the small hs, and that would be your lambda. So the appropriate equation, if you need to memorize, but it's easy to memorize when you understand, is this for energy balance. So you have already two terms on the left side and on the right side of your equation. And just like what I said a while ago, the Q, which is UA delta T, is equal to S lambda. That's the amount of energy that your steam liberates. That way your feed gets concentrated. Now, as to the enthalpy of the feed, I need to emphasize this one. There are two ways of determining the enthalpy of the feed. One is using this formula, and the other one is also using this formula. The third one would simply be a case of reading out HF from the concentration enthalpy diagram. But that won't be any problem because that would be a simple readout. You take it out from the diagram. What about the two formulas that I'm saying, which is using the same representation as this one? You will have the heat capacity, you have the temperature of the feed, and this T sub 1 will be the reference temperature or some base temperature that you will subtract from the feed that later on you will also use as the base temperature in determining the other enthalpies of your other streams. I'm referring to the thickened liquor. If the system that is given in the problem does not have a concentration enthalpy diagram. Because class, the concentration enthalpy diagram that is found in most books in unit operations under the evaporation topic is only that for sodium hydroxide. There's no concentration enthalpy diagram for other systems. So if it's a different system, a different solid, what you need to do in determining the enthalpy is use this formula. So if you use this formula, you have to understand that whatever is the base temperature you use here for the feed, that would be the same base temperature that you use for the thickened liquor when you account for its enthalpy. And if the unit is SI class, this base temperature or reference temperature, if you have a piece of paper there, is 0 degrees Celsius or 0 degrees centigrade. SI. If it's English, it is 32 degrees Fahrenheit. You only use this formula if your system is not sodium hydroxide water, because we don't have a concentration enthalpy diagram for other systems. So you have to use this formula really, because the one that is available in your handbook and in Jan Kuplis and even McCabe is only for the NaOH system and water. So you have to use this particular formula. Take note of the reference temperature. This reference temperature is 0 degrees Celsius for SI and 32 degrees Fahrenheit for English. Now, that's how you determine the enthalpy. Now, this is our sample problem for a single effect evaporator that does not have a boiling point elevation. I will try to go back to that illustration that will determine the, I cannot skip, that will determine the BPR given a particular chart we call the Durings chart. So in now class, what I'll do is I will stop for now because I cannot really escape from my PowerPoint. I cannot go to my Word file. Anyway, there's 3 minutes left. We'll have a break, then I'll go back after 3 minutes. You use the same link for us to start solving and going through the solution of the problem again. Okay? We will just stop here for a while. I will stop recording.